All right, good afternoon. Hopefully quiz 3 went okay. Looks so far that looking at it went okay-ish. I don't know when the TAs are meeting to mark it, but I will update you as soon as I know any more information. So today we're going to be a bit more modern. We're going to talk about SSDs, which people actually have in their machines, and RAID, which is a fun topic. So SSDs or solid state drives are more modern than hard disk drives. There's no mechanical parts. They're kind of like RAM. They use transistors to store data rather than magnetic disks, so you can't actually ruin it with a magnet. So pros, no moving parts or other physical limitations where the spinning actually matters or actually waiting for something to physically move. It's going to be higher throughput. It's going to have good random access, so everything doesn't have to be sequential. Like we saw with spinning disks, if we didn't access it sequentially, our performance went down by like 2 orders of magnitude. They're more energy efficient, again, because we're not spinning a hunk of metal. Better space density, so we can fit more bits of information in a smaller space. But they're going to be more expensive. They're going to have lower endurance, so solid-state devices actually have a limited number of times that you can write to them. And then after that, they wear out, and you can no longer write to them anymore. So there is a level that they will just kind of wear out, and you won't be able to use them anymore. And as we'll see, based off just how they're made and their architecture, they're also more complicated to write drivers for. So this is the architecture of an SSD and what it looks like for the purposes for us. We don't really have to care about the die in the yellow and the plain in the brown. We only have to care about blocks and pages. So blocks aren't exactly what we talked about before. So a block in this, for a solid state device or drive, is a group of pages. So all of the pages luckily are usually 4 kilobytes in size, which actually matches up to our virtual memory pages, which is nice. The not nice thing is that they are organized in blocks, and there are special rules for reading and writing them. So SSDs use like NAND flash. They're going to be much faster than hard drives. Page size will typically be 4 kilobytes, like I said. And then it's going to be about an order of magnitude quicker than a hard drive. So reading a page would be like 10 microseconds. Writing a page would be 100 microseconds. And then curiously, erasing a block is 1 millisecond. And you will actually note here that it is impossible to erase a page. So I can only erase blocks, which is why actually writing drivers for this are kind of complicated, and your kernel actually has to do some special, has to handle these specially in order for it to work correctly. Yep.
What's the difference between zeroing out a page or zeroing out a block, I guess, and erasing a block?
So in the next slide, we'll see that when you write, you're only allowed to write once after it's erased. And then after that, it's locked until you erase it again. So you still have to erase it. So yeah, this is where that comes in. So if you actually program and write drivers for these things, then you have to use pages and blocks. So the rules are you can only read complete pages. So they have to be written to. You can't just read uninitialized stuff. And you have to only write to freshly erased pages. So you can't rewrite over something without doing an erase in between. And erasing is only done at the block level, and a block will typically have like 128 or 256 pages. And yeah, the entire thing needs to be erased before you can do even one write operation. So that is why writing would be slow. So if you want to modify one page that has already been written to, well, you're going to have to, the naive thing to do would be to copy all the other like 127 pages on that block to a new freshly erased block, and then write that modified page to that block, and then update all the information so it points to the new block instead of the old block. So you're going to have to do lots of writes if you just want to modify a single page. So the OS can help with this a little bit, or the kernel. So SSDs will need to garbage collect. Yeah.
Previous page? Sorry, what's the smart approach?
Sorry?
I thought you said the naive approach is to read the entire page and write to a fresh page. So what's the
Well, that's what you have to do. But if you want to just modify a single page, you don't want to just write out 126 of them or 127 of them just to write out one. So we'll see we can do something slightly better. Yeah, the naive thing to do if you want to write something new is you have a freshly erased block, you transfer all of it to a new block and then erase the old block. And then you have to update everything. So we'll see that. So the SSD will need to have to garbage collect some blocks. So like move any pages that are still, so in that worst case I was talking about where we have to move 127 blocks or pages, sorry, that would of course be the worst case. So the kernel, one smarter thing it could do instead of moving all 127, it could just move the blocks that it knows are actually still in use. So that would still be some overhead, but it's at least more intelligent, and we're not just writing, n minus one. So the disk controller also needs some help to indicate what blocks are alive. So even if you have, you used a block, you've written to it, the SSD is going to assume that that block is in use, even if the kernel no longer uses any of those pages anymore. So the kernel needs some way to talk to a disk and tell it that, hey, that block has all the pages I'm no longer using, so you can go ahead, you can erase it at your will so I can write to it again later. So that's what that trim command is. So if you've ever seen that, it's mostly it was an issue when SSDs were new and not every kernel actually took SSDs into account, but now pretty much everything is going to have it. So the trim command is basically the kernel informing the SSD that I'm not actually using any pages on this block. You are free to garbage collect it and erase it. And then the SSD hardware, whenever it would be idle, can just go ahead and erase it in the background whenever it's not doing anything else terribly important. So that's the long and short of SSDs. We won't go into too much detail about them, just really know that you have to deal with, they have the special rules where you have to erase a block at a time. Blocks contain multiple pages, and you can only write to a freshly erased page, and that's about it. And then, yeah, so far we've been talking about single devices. So I guess mockingly, this is just sometimes called a single large expensive disk, or SLED, and you can tell by the kind of wording of it that it might not be such a great idea. So it's just one big large disk. So the naive thing to do again is if I run out of space for all my files, well, I just go buy another hard drive and transfer everything to the new hard drive and just start using that. But the drawback of that, one, it's going to be slightly expensive as you try and get more density. And also, it is a single point of failure. So if you lose data, if that disk dies, then all your data is gone. So what people typically use is something called a RAI, or a redundant array of independent disks. And it's basically just data is distributed across multiple disks. And you can, when you do that, you can give a whole bunch of different trade-offs, whether you want to trade off performance or redundancy in case one of the drive fails, and how many failures you actually want to endure. So one of the first RAID configurations you might see is something called RAID 0. Has anyone ever used RAID before? Probably not. One? Okay. So this is a term if you're like a data hoarder, or if you really want good performance, you would use something like this. So RAID 0 is also called a stripe volume. And all that means is all the data is just put together in kind of larger chunks. and then those chunks are distributed over the disk. So in this example, say file A was made up of 8 chunks. Well, the odd number chunks would go on the first disk, which would be disk 0, and the even number chunks would go on the second disk, which would be disk 1. So now, whenever I need to read a file, well, I can read half from disk 0 and then half from disk 1, and it's going to be twice as fast. And then similarly, if I need to modify it, assuming I'm modifying something that's big enough, well, instead of writing all that information to one disk, I write half the information to one disk and then the other half of the information to the other disk. So your reads improve by a factor of how many disks you have, and so do your writes. So you can do the same idea with more and more drives. So you could do this with 3 drives, 4 drives, 5 drives, but the big drawback is that if any of those drives die, then you lose data because you only have one copy of everything and no way to get it back. So instead of being a single point of failure for one disk, now you have multiple points of failure, which is kind of bad if you actually care about the data. So it's really only for performance only. All the data is just striped or basically just split into chunks and put on multiple disks. So you're going to have faster parallel access. You're going to get roughly n times the speed up for both reading and writing. But any disk that fails is going to result in data loss. You have way more points of failure. So you have n points of failure for how many disks you have, and it only takes 1. So the kind of opposite approach to that, where you essentially make an exact copy of everything, is called RAID 1, and that makes each disk an exact mirror of each other. So if that file now is just 4 chunks, well, if all 4 chunks are on disk 0, then all 4 chunks are also on disk 1. So now, if any of those disk drives die, then I still have a backup, and you can do this for multiple drives. So I could have 4 drives that are all the same, or 5 drives. So this is where the textbook terminology also gets weird. So we'll discuss at the end something called RAID 10 or RAID 1+0. The textbook, when you expand RAID 1, it doesn't just assume every disk is an exact mirror of each other. It goes into this weird alternate thing that we'll discuss later. So just watch yourself if you're reading the textbook. So RAID 1, simple but pretty wasteful. So every disk, again, is an exact copy of every other disk. And this gives us way more reliability. So as long as one disk remains, we have no data loss because they're all the same. So if I have 4 disks here that are all the same, I could lose up to 3 of them because they're all the same. So I can tolerate everything except one disk dying. So it's going to have some good reliability. That's a lot of points of failure that need to occur in order for you to have data loss. And it's going to have good read performance because it doesn't just have to read from one disk. It can split up the reads across multiple disks. And in this example, say there were 4. Well, one disk could send A1, one disk could send A2, one disk could send A3, one disk could send A4. So you could split up the reads across the disk, but you couldn't split up the writes. So it'll have good read performance, but the write performance will be the same because you have to write the data to all the disks, and it might actually be a bit slower if you kind of run out of bandwidth. So, yep.
So read performance is good just because there's if we're reading the RAIDs, one disk has A1 and everything else, but on the other disk we just read A2 and A3 stuff.
Yeah.
But writing we just have to write everything, right?
Yeah, because if I'm writing, say I have 4 disks in this case, if I modify something in A1, I have to write it to every single disk in this case.
Wait, so how is that the same as a single disk performance? Isn't it single disk you just write one of the disks?
Yeah, so you're
We're writing to n disks. Wouldn't have to be.
yeah, so you're assuming the bottleneck is actually writing to the device. So if I write to 4 devices at the same time, it's the same as writing to 1. So that's why I said assume that we have enough bandwidth. Yeah.
Is it because
Yeah, well, you'd issue all the same commands to all the disks. So ideally, all the disks would pretty much be the same, like manufacturer and everything, so they'd all behave the same. So you just send the same commands to all of them.
Right. And then like, so like these disks will be on top of each other in like a physical device, and then there's gonna be heads.
No, so these would be independent disks. So like disk 0 and disk 1 would be two separate hard drives.
Oh,
They're separate, yeah.
wait, so what was the, like, I remember at the very start, you showed like a picture of, or like 2 lectures ago.
Oh,
Then there's like multiple disks on top of each other, and they each have like their own head.
yeah, so there's multiple platters. So that's just the only way to access data on a platter. So one head per platter.
Right, so
But you can
this
only,
is not disk 0 is one platter, disk 1
no.
they're separate.
Yeah, in this case, these are separate. So in this, disk 0 and disk 1, they could be a hard drive, they could be an SSD, they could be whatever.
Also, SSD, you can also use RAIDs.
Yeah. Yeah, you can buy a bunch of SSDs and configure them like this if you want. You can configure a bunch of hard drives like this if you want. Typically, if you do this, you really only care about as much data as possible. So, like, if you care about your data, you go to the store, you buy a bunch of spinning disks, and you set them up like this.
Why would we need RAIDs for SSD if they don't have physical, like?
So if you care about, SSDs will fail too, right? So if you care about your data, you might want that. Or you might want the performance if you want SSDs. So if I could do RAID 0 and get twice the performance as my single SSD, I just buy another one.
So when you have RAIDs, you're not configuring one device. You're saying, okay, let's get more devices.
Yeah.
Let's distribute the.
Yeah, so the idea of RAID is, like in its name, the redundant array of independent disks. So everything's independent, and then you configure them however you want. So we've seen 2 configurations. So there's RAID 0, which is like go as fast as possible. I don't care if one fails, I'll take some data loss. And then 1 is like as safe as possible, everything's a copy. So you can think of this as like, it's one way to think of this is it's like automatically creating a backup for you. So anything that you modify your lab, it's saved on 2 devices. So now if one dies, then the other one, still has your data. You don't lose your lab or anything like that. Okay, so then the idea here comes for RAID 4, which I'm just here for illustration. It's not actually used, but the idea is key here.
Where did 2 and 3 go?
Yeah, question is where 2 and 3 go? So 2 and 3 were large mistakes. They didn't work that well. So we'll skip over 2 and 3. We'll be skipping over 4 because 4 basically doesn't exist either because it's a bad idea, but we'll see. This is how things work. People get an idea.
What does RAID mean in this case?
Same thing, redundant array of independent disks.
Oh,
So the numbers just corresponds to how they're configured. So a RAID 4, does kind of what RAID 0 was doing, where it stripes the data across disks, but instead of here, there's one disk dedicated to parity, and what that will do is basically store some information such that if one of the disks dies, then it can actually reconstruct what that bit was. So the easiest way to argue about it is with bits, so we can see something like this. So say we had, I don't know, whoa, that's thick, 3 bits of information. And then we had 4 drives. So in this case, actually I'll call it 3. So disk 3 is going to be our parity drive, and it's going to essentially be an XOR of everything. So let's say across these disks, we're storing 1, 0, 1. We're storing 0, 1, 0. Then we're storing 1, 1, 1. So the idea here is we have.
sorry, what does this 3 do?
Sorry?
What does this
What do you mean?
Why is nothing 3?
We're getting there.
Oh,
So this is our data across our 4 disks, and we're going to use, data across our 3 disks, and we're going to use the last disk to store some information such that we could recreate the information if a disk dies. So disk 3 in this case will store parity information, will be an XOR of all the bits.
sorry. I just want to ask, because I thought this was 3-bit machine. Why do you have 4 bits?
There's 4 disks here. I'm just saying there's 3 bits across all the machines.
Oh, sorry.
So I'm just illustrating just because I don't want to write out like a full byte. So in this case, so for bit 3, so on disk 0, 1, and 2, well, the XOR between 3 things is basically the shortcut way to think about is it's going to be 0 if the sum of all of them are odd, or it's going to be 1 if the sum of all of them is, it's going to be 0 if the sum of all of them is even, and then 1 if the sum of all of them is odd. So in this case, if we add 1 plus 0 plus 1, well, that's even. So the XOR of all that is going to be 0. So we would store that information on the 3rd disk. And then for the next bit, we have 0, 1, and 0. So that altogether is odd. So that would be a 1, indicating it's odd. And then for the last one, we have 1 plus 1 plus 1, so that's 3, so that's odd. So if we XORed all of them, that would be 1. So, yeah.
So what exactly happens if, let's say, disk 1 just clears that data, like frees that block and then like writes new stuff? Will we have the update free?
No, so disk 1 would die. Yeah, so this is what would happen. Sorry, what was your question?
My question is, if one of the bits fail, how will we know which one failed?
So the hardware will say it fails, or like the kernel will try and write to it, and it won't actually be written to, or it won't respond anymore, or something.
And then so like, let's say one didn't fail, and like, or it went off. It's just that if the parity disk disagrees, does it know where the problem is?
Yeah, well, if the parity disagrees, then there's probably been a failure.
What if the parity disk fails?
Well, then that's okay. Yeah, so that's a good question. If the parity disk fails, well, the parity disk fails, you throw in another disk and recalculate the parities for everything.
So like, how are you sure all the other disks are fine?
You have to trust the hardware that it actually says it. If it works, it works. So these devices will say whether or not they work.
Okay, but like, and then so like back to the question I had. So like, if you modify like the entry in disk 1, right? Then would we have to recalculate 3?
Yeah, so that's a good question. So if I say everything was working fine, if I go ahead and modify, information on disk 1, then I'm going to have to update the parity bit on disk 3. And then similarly, if I change anything on disk 0, I also have to update the parity information on disk 3. Then if I update anything on 2, I also have to update disk 3. So
if it's like in the middle of the update one, the other ones fail, like,
yeah, so there's going to be some concurrency issues here, right? Yeah.
Sorry. Could you explain again, what does 1, 0 mean? Like, what's considered 1? What's considered?
What?
Like, sorry. How does, I read on your slides that it says parity stores XOR copies 1 to 3. Any one copy can be reconstructed. Can you
Yeah, that's what we're doing.
No, but I just didn't understand, how do you reconstruct with your bits again?
Yeah, that's what we're going to do. Okay, so that's what we're going to do. So this is the reconstruction. So let's assume disk 0 dies. So disk 0 is now dead. So just remember it was 101, but not using that information, we can get that back. So disk 0 is now dead. So now it's dead, all the bits are gone. So ideally what you do here is you buy a new disk and then stick it in, and then you can recreate the failed disk 0 and copy it to a new disk. So we can use this parity information to keep track in order to recalculate it. So we have an unknown here. So it's like unknown plus 0 plus 1 is reading the parity bit is even. So I need either a 1 or a 0 added to 1 to make it even. So I need a 1, right? So the bit 3 is definitely a 1 in order to jive with the parity bit there. And then for bit 2, well, I have a 1 plus 0 and then plus an unknown, and that has to be odd. So the only number it could be is a 0, knowing that parity bit. And then similarly for the last one, I have an unknown plus 1, so like unknown plus 2, and then that has to be odd. So if 2 plus some unknown is odd, well, that unknown has to be 1, if it can either be a 1 or a 0. So just knowing what was on disk 3 here, that parity information, knowing it's an XOR, we were able to recreate our we were able to recreate the data on disk 0. Yeah.
So we're always doing this for like only 1 bit, right? Like when you reconstruct this, it's always by 1 bit place, right?
I'm just showing you by 1 bit, but if you do this times 8, it's a byte.
Yeah, could you show bytes then?
Just add 5 columns.
Oh, okay, sorry.
Yeah, so, yeah.
So bit 3 on this 0, 1, 2, and 3, it must know what bit 3 is.
Sorry?
Like when the disks are spinning, like when you say bit 3, they have to like wait for each other to get to bit 3 to do the update.
Yeah, well, so if you're dealing with the hardware, so this is like at the bit level, but you'd be loading it into like a page or something like that, and then writing it back out in page. So
do the spinning have to be synchronized or in some way? Or?
no. You just issue commands to the disks and let the disk figure it out. So in this too, so you can mix and match disks. So you typically, it'll be as slow as the slowest disk. So if they're all from the same manufacturer, they'll probably all behave the same, so you won't have a bottleneck. But if you gave it like, 3 SSDs and 1 hard drive, well, then it's going to be as slow as the hard drive, essentially. All right, so that is the idea behind the parity calculation. But as we kind of discussed, this is not great, because if you modify anything on any of the disks, even if I was to only modify A1 on disk 0, B2 on disk 1, and C3 on disk 2, well, 1 block on each of those disks would correspond to, I have to update the parity information on disk 3, so it's going to do 3 times the number of writes as the other one. So it's going to be very disproportionate, and you're going to get bottlenecked by that parity disk. But that's why it's not used, and I'm only using it to illustrate. But with parity, so you can use essentially all of the space minus the space from one of the disks, and you need at least 3 drives to do this type of, you need at least 3 drives to do RAID 4. So we can get n minus 1 times performance because all the rest of the data is striped, and that's essentially just arguing that we ignore the parity disk, and then it's essentially like RAID 0. But then the con is that that's not actually going to be true, because your write performance is really going to suffer, because any update has to write to the parity disk. But the other pro is we can tolerate a single disk failure with good performance and not wasting that much space. So, but if 2 disks fail, then we're screwed. So RAID 5 is how RAID 4 is actually used. So RAID 5 is exactly like RAID 4. The only difference is there's not a parity disk. It distributes all the parity information across all the disks. So now before disk 3 had the parity calculation for A, B, C, and D. Well, now disk 3 only has a parity calculation for A, 2 has the calculation for B, 1 has the calculation for C, and 0 has the calculation for D. So you're hoping that since you distribute it across that, you'll kind of even out across all the disks that have to update the parity information. So this is the first RAID 5, or RAID 5 is like the first one that's actually used aside from 0 and 1. So 4 is not actually used because it's going to be really uneven on that parity disk. So RAID 5 is basically just an improved RAID 4, all the same pros as RAID 4, except it doesn't have that con where we have probably suffering write performance because we're bottlenecked on a drive. So 6 is like RAID 5, except there is now 2 parity bits. So instead of before where our parity bit was called P before, now we have another parity bit called Q, and then like with RAID 5 to RAID 4, we're not going to have 2 disks that just calculate parity bits for P and Q. We're going to distribute them across all the disks. So your first parity calculation for P would be a simple XOR. If you're interested in the calculation for Q, or the second one, that is where your linear algebra courses come into play, and I won't go over the details. It like somewhat involves a Galois field, so if you don't know what that is, you can learn later. But you have to do some more complicated math if you want to get a second parity bit there. So from a usage point of view, all you really care about is do the extra parity. I essentially lose another disk of space. And again, I need at least 4 disks to do a RAID 6. And also the write performance is going to be slightly less than RAID 5 because I have another parity calculation. And also one thing that's listed on here that is a big drawback too is you might actually care about reconstruction time of how long it actually takes to, make the new disk a copy of what it is replacing. So like when I was doing grad school, I had a RAID 5 array, I was doing my work. One of my drives died, and I was like, yeah, that's okay, all my data is fine. And I can tolerate one drive failure, but sure enough, you buy hard drives together, they tend to fail together. So after about a month, another one failed, and then I lost data. So you want to replace them when they start failing.
Sorry, why can't you use SSD? Why can't you buy SSDs with hard drives?
They're expensive.
Also, if they were expensive like 20 years ago. No,
They're still expensive.
Oh, wait, if you have, doesn't the school give you disk drives?
Some people work it, does the school get it?
Yeah, the school has to buy them. Yeah, drive space isn't free.
Oh.
Yeah, what's SSD? Because I don't even think, let's see, quick Google search. Yeah, they don't even make 12 terabyte SSDs. You can buy I just bought a 12 terabyte hard drive. You can't buy a 12 terabyte SSD. Well, you can, except they're going to be like several $1,000s. So.
Wait, so your experiment in grad school needs like 12 terabytes?
No, in grad school it was less than that. It was
okay.
more, I cared about my stuff not getting deleted. So I had a RAID, and then it died. So replace your stuff, because they tend to fail together. So another...
RAID broke completely?
Sorry?
So your RAID broke down like the parity disk broke?
Yeah, well, so it was RAID 5, so it was like this. So one of the disks died, which is fine. You can still use it because you can calculate all the information on the fly, so you can still access all your files and everything. So I was like, yeah, this is fine. I can still work because it takes like days to rebuild it as well, to recalculate the parity for like, I forget how big they were. Like they were probably like 4 terabytes. So it might take like 4 days to rebuild it. Yeah.
if your disk died, where is it going to put the reconstructed data?
On the new disk.
No, but you only have 4. If one died, where are you going to put the reconstructed data?
So here, if you have 4 disks and one dies, you have 3 disks. So you replace the old one, you put in the new one, and then you have 4 again. Then it has to reconstruct all the information that was on the one that died to the new one.
Wait, so you didn't lose all your data?
Well, 2 died.
Oh, so in the middle of reconstructing, another one died? Or,
I didn't get to the reconstructing step.
oh, so there's 2 died and you lost data for sure?
Yeah, 1 died, and then I'm like, yeah, this is fine. And 2 died.
Oh, so in this case, like the point failure is just 2.
Yeah. So that's why it's good to know this. In actuality, 2 died, but 1 was like just dying, because as soon as 2 died, I ran to the store and bought a new one, and it was just starting to die, so I actually got most of the information off it. So it like gimped along. Yeah.
So if you have a disk die, it's done forever. You can't just erase it and like use it again.
Yeah. This is like assuming disk drive, they can fail in fairly spectacular ways. So like the spinning magnetic disk, one spectacular way they can fail is called a head crash, where that magnetic head hits the platter and essentially makes it explode. And you're not going to retrieve any data off that because it is now in a billion pieces. Yeah.
So for RAID 5, if one of the disks dies and you don't replace it, it basically becomes RAID 0.
Yeah, it becomes a slow RAID 0. So if one of these disks dies, say I don't have A3 anymore, right? In a normal A0, if I just had, normal parity or normal RAID 0, I would have like A1, A2, and A3, and then I could read them all. But if I have this and say disk 2 dies, well, if I want to get A3 back, I have to kind of calculate it back. So it's going to, yeah, so it's going to be a calculation step. So it's going to actually perform a little bit slower if you have 1 dead. Yeah, but remember, like the parity is going to be distributed across, so most of them will probably have the information, but you're still going to have some parity. So it'll be slower if 1's dead. Ideally, you don't do what I do and you go replace it.
Sorry, for your RAID 5, like if your disk is 0 died, you lost a parity bit too.
What?
Like, sorry, if your disk is 0 died, do you also lose your parity bit?
So in this case, if disk 0 died, yeah.
Sorry, I meant the DP.
Yeah, so you would lose all of it, but you can recreate the parity bit because all the other information's still there.
But in your next, oh, okay. Sorry.
Okay, so another thing you could do too is something called, so there's another RAID 1 that is a combination of 2 that's in the textbook. So you can also have something called a RAID 10, or sometimes it's called RAID 1 plus 0. And the idea behind that is that it stripes, but it has 2 copies of everything. So say we have disk 0, disk 1, disk 2. So I'm going to use 6 disks to illustrate this. Disk 3, disk, actually I'll put it to the side. So the idea behind this is for half the disk, you do what RAID 0 does, and you just completely stripe the information. So for example, I would have like A0, A1, A2, and then I could have, the next bits of that file, A3, A4, and A5. So within those 3 disks, they're all striped. So this is essentially exactly like RAID 0. And then the 1 plus 0 is I make a copy of all of that with the other disks. So this way, in this dimension, it's kind of like a RAID 1. So disk 3 is an exact copy of disk 1, or sorry, disk 3 is an exact copy of disk 0. Disk 1 is an exact copy of disk 4. And then disk 5 is an exact copy of disk 2. So that way, now I get pretty good performance, and also if one of the disks dies, so say disk 0 dies, this disk is dead, well, the cost of recreating it is going to be much faster because there's no calculations involved. I just take out disk 0, I put in a new disk, and it is an exact copy of disk 3, and only disk 3. So you just have to copy all the data from one disk to another disk. There's no calculations across disks involved or anything like that. So instead of my scenario where it would have taken days to reconstruct, it only takes hours to just straight copy a drive. Especially if they're a spinning disk, you just copy it all sequentially and it will be quite fast. So now the question for you two is, in this configuration, whoops, I hit that. In this configuration, how many drive failures can I withstand before I actually start losing information? And losing information in this case means that I have one of these blocks where I don't have any copies anymore, or if I had parity, I don't have any means to reconstruct it anymore. So this has no parity, so you can essentially argue about that I don't have any copies of a block left. So we got two minimum, yeah.
If you're unlucky, 2. If you're lucky, 3.
Yeah, so
You can't lose 3, right? You just can't lose disk 1, disk 4 at the same time.
no, so my worst case is if I lose 2 disks, I might be screwed by, if I'm lucky, I could lose up to 3 in this scenario. So why is that? So now let's assume disk 3 dies. So disk 3 is dead. So if disk 3 is dead, well, essentially my danger zone, if you want to think of it that way, is I only can't lose disk 0, because now on disk 0, that's my only copy of A0 and A3. But I could lose any other disk because there's 2 copies of everything else. So if I lose this disk, I'm screwed. I lost, a third of my data and it's no longer there. But I could lose any other disk. So I could lose disk 1. So now we're in a bit more of a danger zone. So I lost disk 1. So now I'm essentially, if another disk fails, I'm essentially assuming everything's like perfectly, randomly distributed or uniformly distributed, I'm at a 50-50 shot now. So if I assume disk 0, 4, 2, or 5 could die next, well, if disk 0 dies, well, I'm screwed because now I don't have A0 or A3. If disk 4 dies, I don't have A1 or A4 anymore, but either disk 2 or disk 5 could die. So if one of those dies, then that's fine. And I still have all the data, but now I don't have any backup copies of anything else. So because there's mirrors of everything, so if I lose both mirrors, I'm done, but I can, if I have one failure in every stripe, that's fine, I can go with that. So this is going to extend up to, like, if I have 8 disks, I can tolerate my minimum 2 failures, because you're still, no matter how many you have, if both pairs die, then you're screwed. But I have more pairs, so I could, if I'm really lucky, tolerate 4 failures if I have 8 disks, for example.
4.
Yeah, so if I have 8 disks, it'd essentially be like two more here.
Okay, so like the max amount we can tolerate before failure is number of disks divided by 2?
Yeah, so because they're mirrors, so if you got really lucky, the most amount of failures you could tolerate is the number of disks divided by 2, but your minimum is always 2 because you could knock out the other mirror. So it depends kind of how lucky you think you are. But the nice thing about this is to reconstruct it, again, it's really, really quick because I don't have to do any computation or anything like that. But of course, if I have, one of the big drawbacks though is essentially I'm wasting half the space just for the mirror. So the more disks I have with RAID 5 and RAID 6, the more space I get back, like closer to the theoretical max if they were all in RAID 0. But in this, your capacity is always going to be half. Yeah.
Could you do something like buy really reliable drives with one half of the mirror and like cheaper, crappier ones for the other half?
So, yeah, so the question is, could I do really reliable ones for half the mirror and then unreliable ones for the other half that are cheaper? I imagine you could. There's more exotic file systems if you really care that can do a bit better than do the parity a lot faster. And typically at that point you're wasting your money on really reliable drives. You'd be better served just to buy more. Yeah.
How long does it take for the disk to fail? Because I've never had any failures.
So the question is, how long does it take a disk to fail? So I mean, there's a distribution of failures. Within off the top of my head, I mean, it really depends on what drive you buy and who makes it. But the average failure rate for 2 years, ballpark, probably 5%, something like that. So if you are Google and you have, thousands and thousands and thousands of drives, you're going to be somewhere in that distribution, and a lot, 5% are going to die within 2 years.
I got pretty lucky.
Yeah, so I've had drives I've been lucky. Some drives have lasted, 8 years. They still work, 12 years, who knows. The drives that died on me, they were it was warranty time plus 2 months. So I think it was they died after a year and 2 months. So I got unlucky. That was a notoriously bad batch, and now I just don't buy drives from that manufacturer anymore. So, sorry? Let me turn this off and that'll say. All right, so more options for persistence. So we saw SSDs and RAID. SSDs more like RAM, except access is in page, and the only difference is in blocks. And because of this block thing where you need to erase it, and you can only write to a freshly erased block, and you can only erase groups of pages, the kernel and the SSD kind of have to work together using something like trim. And we saw RAID to tolerate failures and improve performance using multiple disks. So that's it for today. And just remember, I'm pulling for you. We're all in this together.